I also would like to thank the organizers and particularly Dimitris for putting together a very interesting meeting. And needless to say, I also like very much the location. So I even was tempted to put here July 2016. So it's likely that this number could be changed as well. Yeah, so what I want to talk about is a quantum simulator idea, and so this is about putting together two areas that have been covered in tutorial lectures here in this meeting. So topological order and quantum information in that by Yanis Pathos. So unfortunately I wasn't able to attend his lectures, but I'm sure he introduced tutorial code in some detail, and my aim here is presenting a concept to realize this, Hamiltonian in superconducting circuits. So that's the technological platform that Andreas Waldorf was introducing here, and I make use of the building blocks that he was talking about. So I want to start out by what is probably very much a recap of what Yanis was talking about, so introducing topological order, and then like the definition that I use, and then talk about how we think about implementing this. So in a three-dimensional system, topological order appears if it has the following properties. So there should be an almost degenerate manifold of states that are separated by an energy gap from excited states. So like I try to draw this here. And the degeneracy of this ground state manifold should only depend on the topological properties of the system. So not on anything that is related to size and distances. And then a local operator cannot distinguish between any of these ground states. So any local operation on one of these ground states will actually get you up into this excited state manifold. Yeah, so there can be no transitions between these ground states just by applying the local operation. And that's why these systems have become received interest in the context of quantum information processing. So the idea here is to use this degenerate or almost degenerate ground state manifold as the logical qubit. And then because a local operator cannot do any transition between the two ground states, applying it onto one of the states in the ground state manifold will always generate one of these excited states. And so there is therefore for local errors an energy penalty, because the force that acts on the stored quantum information needs to be strong enough to overcome this energy gap. And then there can also be no transformation between the states in this topologically ordered manifold just by a local perturbation. So you really need a non-local operation to do any transition to this topologically ordered manifold. So the really standard model of this tutorial code. So this is a 2D lattice of spin 1/2 degrees of freedom. By drawing this here in just grayscale, I want to indicate that I am assuming here periodic boundary conditions in both directions, so that this is actually on the surface of a torus, hence the name also toric code. And now these spin 1/2 degrees of freedom interact in so-called star and tangent directions. So I've highlighted this here in red. So this is a 4-body interaction, and in the notation that I use, a star interaction is here a product of 4 sigma x operators. So these are just Pauli operators on the spin 1/2s. The tangent interaction is a product of 4 sigma y. So the important thing is, of course, that these two are different. And then the toric code Hamiltonian is just a sum over all possible star interactions and all possible tangent interactions. And the typically interesting regime is when this Js and Jp are the same. And so one reason this model has become very famous is that you can also nicely solve it. And that is because all these so-called, so these are also called stabilizers. So maybe I should say, so there are two approaches to the toric code. So one is about implementing its Hamiltonian, but of course in terms of quantum error correction, you can also think of you just measure these stabilizers and that projects the state to these ground state manifolds. So I'm here focusing on the realization of the Hamiltonian. Yeah? And so hence this so-called projection measurements, that's why these operators are called stabilizers. And a nice property of them is that they all commute with each other. So this is very obvious for the star operators among themselves and the bracket operators among themselves, but that they also mutually commute is because when they touch, then they have two spins in common. And that's why this. So a consequence of that is that the ground state should fill because of this minus sign zero property that it's an eigenstate of all the star and all the bracket operators with the eigenvalue 1. Yeah. Then you can ask yourself, okay, what's the degeneracy of this ground state manifold? Well, so if I have a lattice which is L by L in size, then there are 2 to the times L squared physical spins. And then the Hilbert space is, of course, of dimension 2 to this power of this N. And then for each of the stabilizers, I have a condition. So each of these conditions should actually divide the number of states by 2, right? Because it selects either minus 1 or 1, so it selects the plus 1 from the two possible things. And you might think, okay, so if as I have n, 2 to the n physical states, and each condition reduces it by a factor of 2, so do I only have one ground state? No, that's not the case, because not all these stabilizers are actually independent. So if you do the product over all stars, this is an identity, and the product over all brackets is an identity. So the actual number of ground states is 4 here on this torus of periodic boundary conditions in both directions. And this nicely shows that the number of ground states actually depends on the topology. So it's only determined by the boundary conditions. Right? So, and what about excitations in this toric code? Yeah, so you can of course see that each spin here either belongs to 2 stars or 2 brackets. So if you apply a sigma y, for example, on one of these spins, then it creates 2 excitations in its adjacent stars. So these are what I'm calling these electric charges. And similarly, applying sigma x here would generate 2 excitations in adjacent brackets. Then if the others are called charges, then these are called rotating vortices. And if you do then a string of such, say, sigma y's here, then this moves these excitations apart. And then there can be 2 things. So if you move them along such a so-called reducible loop that you can contract to 0, then this is an identity. But if you do this along an irreducible loop, so along the periodic boundary here, so I've drawn this here again on the torus. So one of the irreducible loops is this one, and the other one is that one. So this cannot be shrinked to 0. Then these transformations actually transform one of the topologically ordered states into another one. And the interesting thing of if you move an electric charge around a magnetic vortex, then you pick up a non-trivial phase. And that's why these are an example of median atoms. Yeah? So these are like the interesting features of this toric protocol. So let me say a few more things about why topological order is something interesting. So in the toric code is like considered the standard model for those. So these topological phases appear. So prominent candidates are like fractional quantum Hall systems and spin liquids. This is the class to which the toric code also belongs. These topological order states are locally indistinguishable, and therefore if you study phase transitions, they cannot be a local order parameter for those. And moreover, they have a property that the ground states have actually a higher symmetry than the Hamiltonian, and that sort of fundamentally distinguishes it from the class of systems that can be described by a Ginsburg-Landau theory of symmetry breaking. Yeah? So that's the line here. So it's an interesting and novel class of order, which has intriguing quantum correlations and entanglement and exotic excitation in the form of these angles. So I think, yeah, it would be desirable to have a quantum simulator for such a class of systems, and I'm here presenting the concept to do this with superconducting circuits. So So, a few introductory things about the superconducting circuits and why I believe it's a very suitable platform for doing this. So one thing is the excitations or electromagnetic excitations here, so microwave photons, and that of course will mean that I will be addressing non-equilibrium systems here, so I'm not going for photons in the ground state. In the approach that I'm choosing, I'm aiming at keeping the circuit simple, so it will consist of transient qubits that are connected by what is often called tunable couplers, and these are now being developed or are readily available in many of the leading labs in this technology. And while keeping the circuit simple, I make use of the properties that this can be driven in a suitable way. So in particular, these tunable couplers are often implemented as squids, and then you can tune a squid by threading a magnetic field through it, and then can have a constant component, but also can have time-dependent components, and that's what I'm going to use. And two further important things, so if I want to test local indistinguishability of states, I should be able to have local addressing, so single-site addressing, and that's nicely offered by this technology. And the other important thing is that one can build systems with periodic boundary conditions, which is maybe rather unique for all, among other quantum simulation platforms. So this, of course, doesn't come entirely for free, so what we build is we build this so-called air bridges where conducting lines cross other conducting lines, but that's also something that is like a standard thing right now. Alright. So how do I want to implement these spins? So of course each of these spins will be implemented by a superconducting qubit, so formed by a Josephson junction or two junctions in parallel forming a DC squid so that it's tunable, and this DC squid is shunted by a capacitance, and then they have a token describing this building block is the standard thing. So this here is the charge energy that just describes the Coulomb interaction between Cooper pairs on both sides of the capacitance, on both sides of the junction, and there is the Josephson term, which describes the tunneling of the two Cooper pairs through the junction, and this Josephson energy is tunable via this applied magnetic field. And so I'm considering transport type qubits, in which case this qubit can be modeled by a nonlinear oscillator of this form. As I said, its transition frequency is tunable by the applied magnetic flux. And I'm going to consider a regime where this charging energy will be large compared to all the interactions between the qubits that I introduced now. And so it's a good approximation to treat this qubit as a two-level system. So only the ground. Yeah.
Is it really negative?
Yes, yeah. So it would be positive for a pi junction, okay. But no, it's always negative. So, yeah. So how, the crucial point is how to implement these interactions, in particular the forward interactions. So there's the circuit element that we are considering to do this is a DC squid, possibly shunted by a capacitor. So I brought this to represent that the Josephson junctions always have a non-negligible capacitance. So these black dots are the qubits, and they are modeled via a DC squid that is connected with inductances to these qubits. So let me zoom in on this a bit more to explain it a bit more. So the qubits are described in the phase degree of freedom. So their phase varies by 1 to 5, 4, describing these 4 qubits that form part of this forward interaction. Each qubit has this circuit, so this upper node is actually connected to this inductance, as a circuit as I introduced it before. All these inductances are of the same inductance value, and then there's this DC squid at the center, so each junction has a Josephson energy J, and there comes a capacitance with each junction. I have drawn this here as a shunt capacitance. And then the crucial thing that we're going to do is drive this coupling split not only with a constant magnetic field, but also by oscillating AC field. Yeah? And what you of course see that there are like two auxiliary nodes that appear when connecting these two qubits to each port of this and they should not feature in the final model, so they need to get rid of these. So find conditions under which we can eliminate those from the description. So what's the Hamiltonian that describes the circuit? So for describing the split element, it's actually best to consider like the center of mass on the breathing node for these two auxiliary nodes here. That's because the center of mass node, it doesn't talk to the Josephson energy and it doesn't talk to the capacitance here. And that's why it will typically be at a very high frequency, and I'll forget about this one in my presentation here. So we don't do the calculation, but we usually take the simplified quantities. So then the inductive coupling here between the squid and one qubit is of this form. So this is just the energy of an inductance, the difference of the two phases. So the phase variable describing the squid and the phase variable describing the qubit appears here. And then I expand this so that I get the local terms and the coupling terms separated. And for the squid itself, it also has like a charging energy, which is due to the capacitance associated to each junction, and it has the Josephson energy. Yeah? And now, so what we do is that the flux bias on the Josephson energy, we choose it such that the constant part of the phase associated to it is high. So effectively, this means we suppress the critical currents in the squid. Yeah? And then there's also an AC part, so a time-dependent modulation on that. So then, what this means is that this squid mode is actually nothing but a harmonic oscillator with an oscillating drive applied to it. Yeah? And the coupling term is here from this part. So I should say of the squid, the potential energy comes only from its coupling to the neighboring qubits. Yeah, that's because I have suppressed its critical current. Right. So now what is the crucial concept for getting this four-body interaction? So to like illustrate this, I have drawn something that is more of our everyday world. So these are all harmonic oscillators instead of the qubits now. Yeah. So each qubit, say, represented by some ball that's attached with a spring to a wall, so it's a harmonic oscillator. And then the squid is also a harmonic oscillator, but all its potential is from the springs connecting into the qubits. So it doesn't have any spring that connects it to a solid support, right? And then I look at this in a rotating frame, so each of the harmonic oscillator has then like an annihilation operator that rotates with the frequency, its oscillation frequency, and crucially I assume that all these oscillation frequencies are different from each other. Yeah? And then what I do is I drive the squid, so I take the central mass there and shake it at a specific frequency. Yeah? And I choose the frequency such that the frequency at which I shake is not its own oscillation frequency, so it's like an off-resonant drive. And also the oscillation frequency of the squid is not equal to any of the oscillation frequencies of the qubit. So they wouldn't really talk to each other. And now I shake the central guy. Yeah? And of course, if I, for example, shake it at a frequency that is the sum of all the transition frequencies of these four oscillators, then I will trigger a term where I generate one excitation each of them. And I can take, as another example, I can take a frequency for shaping it, which is omega 1 plus omega 2 minus omega 3 minus omega 4, and then I will generate this over interaction.
I'm sorry, I missed something, but why you call them harmonic oscillators?
So because I wanted to do this everyday example that you have some spheres that are connected by springs. So this all applies to qubits, but I just thought it's like illustrative too.
So you're only going to consider them in the first excitation?
Yes. So if I go to the qubit subspace, this will be a product of sigma pluses, but the same thing works equally. And this will be to the 2 sigma pluses for the first two guys and 2 sigma minuses for the other two guys. But just to make that you can really picture what I want to do. Yeah. So I hope it doesn't confuse you. Yeah. And so, of course, so the drive that I apply to the squid, or say the shaking that I do this is a signal that is composed of several frequencies, and this composition is such that it actually generates precisely the stabilizer interactions that I want. Yeah? So that's the signal I said earlier, so I want to keep the circuit simple because building circuits is difficult, but shaping such a signal is something that is more difficult. Yeah? So to make it a bit more technically, so how do we derive this? What I just sketched, so you need to do an adiabatic elimination of the split qubit. And the coupling between the qubit and the split, as I introduced it before, is this product of the two phases, so you can think of its position-position coupling. And then the elimination, you can do this with the Schrieffer-Wolff transformation, and then the generator of this transformation should have this form. And that eliminates this type of coupling and generates actually a term where you have here this, this drive of the split times a combination of the qubit degrees of freedom to the fourth power, and that will give rise to this four-body interaction. Yeah? And since the split frequency is detuned from all the other frequencies in the game, you can the split will remain in its ground state, and one can replace this cosine of the split variable, and can replace this with this ground state expectation value. And then, so if you expand this term, you will get a product of phi 1 to phi 4, so that will contain the stabilizer interactions that I'm after. We also have two interactions. And further terms of fourth power, but here I connect all those where two of these indices are identical, so these are actually three-body terms, yeah? But of fourth power in this case. Now, if I include this time-dependent factors here that contain the information about the drive, and no longer consider harmonic oscillators, but do this approximation that I can approximate each structural qubit by a two-level system and go to a rotating frame, I get this expression for the phases. And then looking at this first term, and in the rotating frame, I have the time-dependent prefactor, and each of these combinations, where A, B, C, D take on the value plus or minus, will oscillate with that frequency. And then I will choose the frequency composition of the drive such that I trigger a linear combination of these coupling terms that is exactly corresponds to the stabilizer that I want to generate. Yeah? And the same thing will actually show that these two terms are negligible in a rotating ring approximation. Alright, so to do this, I need to have two versions of this time-dependent drive. So I write this as an amplitude times the term that contains the time dependence. And there's one Fs and one Fp, which, so these terms contain 4 drive frequencies each, and in one version, half of these frequencies come with a minus sign, so a phase offset of pi as compared to the other version. And that will make the difference between star and stabilizers. Then all the transition frequencies of the qubits are different in this 4-qubit cell. And this drive Fs will trigger a star stabilizer, and the drive P will trigger a cat stabilizer. So what I imagine is that I drive all these splits with this with a drive that contains 8 frequencies, and when I drive a maquette, then 4 of these frequencies have a phase offset of pi as compared to where I drive this star interaction. Yeah? So that's completely encoded in the drives. Yeah, so to sum up, so this part of the interaction mediated by the split contains the desired 4-body interactions then, plus some terms that are fast rotating and can be neglected. Then there are also fast rotating 2-body interactions. One can even compensate some media contributions by putting additional capacitances here between neighboring pairs of qubits. And so the remaining fast rotating terms, you can show that to leading orders, these will lead to some frequency shifts, but these can be compensated for by choosing slightly different frequencies for the drives. Yeah? And so what you end up with is a realization of this toric Hamiltonian in a frame where each qubit rotates at its own transition frequency. Then, of course, an important thing to ask is also what is the strength of this stabilizer interaction. And the formula is quite simple, so of course it depends on the ground state expectation value of this difference mode on the spin. Then of course on the Josephson energy of the spin, on the amplitude of my time-dependent drive. And this quantity here is of course just the zero-point motion amplitude of each of the qubits. Yeah? Which end is here as well. So one word of warning concerning this rotating frame. Since this is a realization of this toric Hamiltonian in a rotating frame, it doesn't have the simple part of the error protection that a ground state topological order would have, right? So these topologically ordered states are here not the ground states of the spectrum. So they are ground states in a rotating frame, but of course in the lab frame that doesn't mean that they would be ground states. So it has like the interesting part of the topological order that no local transfer operation can transform one topologically ordered state into another one, but it doesn't protect from a local operation bringing you out of the topologically ordered manifold. Yeah, so that's why I wouldn't sell it as a quantum memory, but just as a quantum simulator for exploring topological order. Then of course, one thing that for doing an experiment you would ask is, okay, so how many qubits do I need to build and how large does this need to be? So the fortunate, because of course, since this will be built on a 2D chip, the complexity of building it will grow with lattice size. But the nice thing is that the smallest version that you can do has only 8 qubits. Yeah, so this is sort of below the size that is currently, so below the currently largest chips, which are 9 or above. So I've drawn this here. So each of the black squares is a qubit, and the gray ones again indicate periodic boundary conditions. So this gray guy is actually the same as this one. And the diamonds, so the orange ones indicate the star interactions, and the green ones the magnetic directions. So this has 8 qubits and 8 of this coupling spins. Yeah. So, like currently the largest chips have 9 qubits and 18 plus. So it's of this size. Now, okay, so what would the parameters be? So in this 8 qubit implementation, as I said, all the frequencies of one. So here it's actually for this magnetic direction need to be different. But in order to avoid like higher order two-body terms to neighboring plaquettes, the neighboring plaquette they should be shifted by a smaller amount. So you need for this 8 qubit realization, you also need 8 different transition frequencies. The oscillation frequency, so maybe I should call this delta frequency actually, of this chip in this example of the coupling spins, they can be all identical. And here we have chosen this to lie between these lower frequency qubits and the higher frequency qubits. So the important thing is that it's sufficiently tuned for both. And what like parameters for capacitances and inductances do you need? So the qubits should then, for realizing these frequencies, should have capacitances between 25 and 90 femtofarad, and the Josephson energies between, let's say, 10 and 30 gigahertz. For the squids, the capacitances are lower, and the Josephson energy is in the 8 to 10 gigahertz range. So one thing that is a bit challenging at this point is that these inductances need to be rather large, but there are ways to build such large inductances as so-called superinductors. So this would mean that the inductance is not just a coil of wire, but is a Josephson junction carrier. Yeah, but it's so I think there are inductances of 250 diameter. So for that like set of parameters, the strength of these four-body interactions would be 2 megahertz in natural frequencies. and residual two-body interactions, so that the parameters are chosen such that the two-body interactions are suppressed to as good as you can, or like as far as we have optimized so far, would be like an order of magnitude smaller, and for like very good coherence time, so say T1 and T2, 50 microseconds, there's even a factor of 100 with the strength of the four-body interactions and the dissipation rates. So then, of course, like given that you could build a circuit that has these properties and you could simulate toric mode Hamiltonian, so one question is, of course, okay, how do I prepare this massively entangled topologically ordered states? And one question that you can consider is that you first switch off this time-dependent driving of your coupling splits, which then means the temperature of the cryostat will initialize all qubits in their ground state. Yeah? So that the initial state of all qubits in their ground state. And then you start driving these coupling splits initially with some detuning from the qubits, and then ramp up the drive and decrease this detuning. So this would mean that you have a time, so what you want to do is an adiabatic sweep from this simple product state that's initialized by the temperature of the cryostat to one of the topologically correlated states. And so this ramp of the drive generates a Hamiltonian where you have a time-dependent detuning for each of the qubits and time-dependent interaction strengths for the stabilizers. Start with a maximal detuning and ramp this down to zero and at the same time increase the stabilizer interactions. So this like sweep through quantum phase transition, so has been, or this way of adiabatic sweep has actually been proposed by Hartmann and Dark.
So the drive in the second step is not the drive into the speed?
And they are both it's both the drives in the squid. Yeah? But the frequencies at which you drive the squid that set the frequency for the rotating frame. So you tune the frequency and the amplitude of the drive. But it's only the drive in the squid. Yeah? And since you always look at the rotating frame, this makes the detuning of the qubits. Okay, so you can model this as like tuning a parameter lambda from 0 to 1 that ramps down the detuning and ramps up the four-body interactions. So I've done this here for 2 megahertz of the four-body interactions as achievable, and then assume that initially, so for this plot we do a detuning of 5 megahertz. And then the spectrum of this 8 qubit toric mode looks like that. So what I want to do is start with this trivial state here, and ramp into the manifold of topologically ordered states here. Yeah? So then what I do to test this is I calculate the fidelity of being in this manifold, so just the overlap of of the evolved state with all the topologically ordered states, because I cannot tell which one I will prepare. And to test that I prepare only one of them and not just a mixture, I look at the purity. And then that is a result of this simulation. So this here is this fidelity. That's the time of the ramp. And that's the initial tuning in the and here this is the purity. And you can see that you can have fidelities above 90% and purity is above 90%. So, yeah.
Now, I have a question concerning your previous slide, where you have the spectrum.
Yes.
Actually, this is the spectrum in the rotating frame.
Yes. Yeah.
Yeah, but because you have a periodic impedance system, you need to consider the holding to the Lagrange zone in the context of the theory. And you have 2 to the 16 states. And you need to pack 2 to the 16 quasi-energies into the first Lagrange zone.
So,
actually, that remains that you have
Can you go to the microphone?
the question is that these are the eigenstates of the effective Hamiltonian in the staging frame.
Yes.
But in the context of project theory, you need to consider the quasi-energies of that. So actually, you need to fold that step from the so-called rebound zone, which is defined by the driving frequency. And you have plenty exponentially many states. When you fold that into the rebound zone, the gap between the ground state and the first expected state becomes exponentially small due to the big amount of layers you have. How you do this adiabatic following of the ground state if you have exponentially small gap? Is that possible with your implementation or?
So I'm not completely sure I get the question. So
It's because when you have a real quantum system, you introduce this concept of quasi-energies. And they are not uniquely defined. You need to follow this spectrum you have in the so-called Brillouin zone. So you have these quantum resonances that might affect the adiabatic following of the
okay, so this is just done in the rotating frame.
Isn't that correct?
Yeah.
But if you diagonalize this on the superbit theory, this is the so-called quasi-energies.
Yeah.
What's the drive frequency? Is it that constant or is it time dependent? What's the drive frequency?
So here there is no oscillations in the simulation. It's just that. So basically, these parameters are tuned in time.
What's the drive frequency? Is it gigahertz? What frequency?
The drive frequency, so that should be so separate gigahertz.
There's no folding in this energy scale. There's no folding in this energy scale.
Yes.
Yeah, so I think that so this should connect to why the whole approach works, right? So because then the effective Hamiltonian would look like it does, right? So there must be like a clear frequency separation between these interactions and the drive frequency. Okay. Sorry. Yeah. Okay. So then, okay. Now I've addressed how to engineer such a Hamiltonian, how to prepare a topologically ordered system. So what can you measure on that? So on a torus, you have 4 of these topologically ordered states, and they should be locally indistinguishable. So measuring the local, so single split quantities shouldn't tell them apart. But one should be able to distinguish them by measuring such spin-spin correlations along these irreducible loops. So say a product of sigma axis along such a loop or such a loop. And transitions between the states can also be done by applying Pauli operators along one of these irreducible loops. So if I wanted to do this for the minimal model, then I can test like the local indistinguishability as before. Measuring a correlation along an irreducible loop here becomes much more simple because it's just a 2-qubit correlation. Yeah. So I would need to measure 2-qubit correlations to tell differences between these topologically ordered states. And so a protocol that I could run would be the following. I prepare them, or one of them, via this adiabatic suite. Then I measure individual qubits and these 2-qubit correlations. Then I apply 2 Paulis along the same irreducible loop, which should get me to a different topologically ordered state. And I measure again the individual qubits and these 2-qubit correlations. And whereas the individual qubits should then still give the same result, the 2-qubit correlations should be different. Yeah, so that would be a protocol for testing topological order. Yes, so with this I'm done. I should emphasize, so what I've been talking about is the PhD of Hartmann Samedi. So he's really the driving person behind this. And the project also profited from collaboration with one and Dan Brown at UCL and Anton Tornik, who is here, and Andreas Waller at ETH. And as a reminder of what I talked about this picture, so a way of realizing that for a code Hamiltonian
states that you prepare are ground states in the rotating frame, right? Okay. So, but if you consider the losses of these excitations, is the toric code protected with this particular?
No, so that was my point in this one slide.
Okay.
So it has the difficult part of the protection that no loss would protect you from one topologically ordered state to another one, but the losses can certainly take you out of this band. Because in this version it's not a ground state.
So basically the Victorian is the toric code rather than this. So in general, the problem is it possible to create a generalization of the Kikaev code, but for the Lubinian, because the code of the toric code is for the Newtonian.
Yeah.
So an open problem I see to transpose also this.
So
Yeah.
This is open system.
So yeah.
But you studied the fidelity.
So it is in this preparation, yes, so that, well, not as a function of it, but it's taken into account. So this is calculated for T1 and T2 times microsecond. For example, like the decrease of purity is basically only due to that. Yeah. It's yeah. So I think there have been 60 microseconds. Depends on the demonstrated or so, but it's not. That is not an IQ. The optimistic thing is having 50 microseconds of AQ at the same time. But well, so if you can do, I don't know, if I would do this for 10 microseconds or so, then it would look slightly worse. But also it's not that it completely breaks down.
My question was how related to the buffer calculations.
So that, yeah, so the values that I've quoted, you don't need to exactly hit them. You could also, and there are also some background numbers. Yes, so there is an optimum when all your tunings are best, and as you move away from this, then it gets absolute worse. So, like,
Very simple question. You should how to build up your star rainbow. You put all the pockets and how to use this pockets and how do you demonstrate graphically and pockets and then spend pockets and stars to do. You understand its necessity.
Okay, so the plaquette is built in the same way as the star, just that out of the 8 frequencies that the drive on the coupling circuit contains, 4 have a shift of pi as compared to the star direction. So of course, this also is consistent with what is star and what is plaquette is completely dual. So it's just where I draw my lines. So if you wanted to move so for testing commutation relations of like what is called electric charges or magnetic vortices, so it's single qubit operations. Yeah, so you need to do a sequence of single qubit operations and then measure single qubits afterwards, or 2 qubit correlations. So okay, I have like I didn't figure out in detail what you need to measure to see, but by measuring the 2 qubit correlations and single qubit properties, you should have everything.
The reason why I'm asking is that because it's such a complicated brush,
Yeah.
what kinds of approximation, I think that would be interesting to check because it's a very important problem.
So your question is whether the single qubit operations work in the, like, if they work, if I assume the approximation is okay, they will work. Yeah. You say if yeah. Okay. So yeah. So okay. not do that exactly, but so.
There was another question?
The drive phases, is that
Yes, it's just the phases of it. So stars and maquettes are distinguished by a relative phase of pi for half their frequency.
But the overall phases of different drives for each other.
Yeah, so they should be in phase then, right? So because, I mean, if I, at this star interaction, I have a drive that generates this star interaction. If the drive for another star interaction somewhere else in the lattice is not in phase, then this will not necessarily be a star interaction. Yeah. So probably you could do even more general things than just mechanical star interactions by choosing yet a different. So the concept can generate any interaction term that contains a product of all parties on these adjacent spins. Yeah. So and then you can play around with like amplitude and phases of the frequency components of the drive.
So this would be this model. I mean, how does this actually affect because
so that all the drives are in phase? Okay, I guess yes. So so there's one thing. So one approach could be that the control lines should have the same length and come from so the same length after a beam split. So if you don't manage to do this perfectly, I only have a partial answer to that, and that is also because on the say on the many-body physics side, I think so. Well, or maybe this is a question that I have. So in asking around, so what has been considered is taking the toric code Hamiltonian and just local spin terms as a perturbation. So basically, the guy that I start from is so something like that. Yeah. So and people have considered like how large can this one be before breaking the topological order. But I haven't found anything that considered perturbations that are two-body interactions. And what you are saying that if I don't manage to make the phases right, then I would actually have perturbations that are three-body or four-body interactions. And so, as I mean, I have asked around a few people, including Yanis, and it seems to be a topic that is not yet addressed, probably because the experimental relativity question wasn't really there. You could possibly start to build that. Yeah.
Question?
One in regards to the last comment. There is some work in 2014 by Daniel Loss and Hartmann on this speed model and similar to the expansion of this shaper transformation, and they get this from two-body speed model to similar type of interactions, like four-body interactions. Is this related from the significant perspective?
Exact relations, I don't know.
They do similar to the expansion, but they start from the speed model.
Yeah.
Start from the transform, I guess.
So it's not the same. Well, so it's not. So that just considers like how to transform two-body spin interactions into effective four-body interactions.
Yeah.
Okay, so I will need to check again, but I think there is not this driving element. Yeah. So it's also not in the rotating framework. Yeah. I don't know whether it's really addressed, like whether this has an experimental.
I think it's a general paper, but it's also the transformation which can start to this spin and perturbative expansion.
So there is a direction of research which people call perturbative gadgets but on a more abstract level, derive properties of many-body interactions from properties of modes. yeah, so let me see if I can, I don't know where I have the slide. So, yeah,
I guess I mean outside of the 2-qubit space. You have this, you're assuming that it's a qubit, but there's I guess other states.
So if I would consider higher excited states of each transmon, okay, so from the things we have looked at, it's not the leading perturbation. Yeah, so I would say that the strength of the residual two-body interactions that I've quoted is definitely larger. I can give you, but it should be more than an order of magnitude less.
I didn't understand why you needed large inductance, and you suggested to use this array substitution junction.
Yeah, so actually the large inductance ties to the previous question, because the interaction by the inductance is like 1 over L, 1 over the inductance value. So if I would choose a smaller inductance because I have like a galvanic connection between the qubit and this grid, this would generate a very strong coupling between those. And I'm afraid that I would need to, the two-level approximation for the qubit would break down. And suggesting closed junction arrays is a pure matter of size. If I would, so Anton, you have estimated this at some point, if I would do this in coils, then the inductance would eat up half the chip or so.
Okay, I think we can close the session. Thanks to all the speakers for the meeting.